Hello, everyone. I'm just gonna start in a couple of minutes. Sorry for the delay. I'm trying to help like a few students who couldn't enter. If you could just give me 2 minutes and then we will start, okay? Right. So today we're working on the second topic of this syllabus, chemistry. We're going to be working on what we call the methods of separation. How do you actually, if you have like a mixture, how are you supposed to purify or get a pure substance out of a mixture? Now, this is something we do almost every day. Like if you're familiar with kitchen work, you do that with filters. If you ever made coffee, we always do something like filtration, which is more or less what we're going to be doing today. So again, this lesson is about what? It's about how could you possibly get pure substances out of impure or mixtures. Now, why we're so keen on the issue here? Why are we so keen on purification of substances? The reason why we're very keen on this is because any impurity in foods, medicines could cause serious health problems. So food industry, pharmaceutical industries, medicines are very keen on purity. So if there was any impure or toxic substances, that would cause health issues for many people. Now, before we get any further, I just want to show you like 3 tools that we're going to be using throughout the year. Those 3 tools are all of which are needed for what? They're all needed for like measurement of volume. The first one on the left is the measuring cylinder, right? What's that measuring cylinder for? Measuring cylinder is meant to measure volume of a lot of liquid. So the good thing about measuring cylinder is that you could possibly measure a lot of volume, right? And the good thing here is that it's quick. So you could measure up to, sometimes you can measure up to 50 centimeter cubed very easily. The only drawback or the only problem with measuring cylinders is that they are not accurate. They're more, the measurement, it's rough, or we call it usually approximate measurement of volume. Someone asks you, measure 50 centimeter cubed accurately, you should not be using the measuring cylinder. So the problem here, just gonna write that it's not accurate, all right? What about pipettes? Pipettes are good because they're super accurate. So you can do very accurate measurements with a pipette. The only problem that we have here is that pipettes are actually like limited with volume. With a pipette, you can only measure 25 centimeters. You see that sign I have here? This tells you what? This tells you that you can only measure this much volume, nothing more, nothing less. So you can't measure 24 centimeter cubes. You can't measure 26 centimeter cube. You're only supposed to use that 25 centimeter cube. So again, if someone asks you, measure 25 centimeter cube, the pipette is your method of choice because it's easy to use and it's super accurate. But as I said, it's limited to what? Limited only to 25 centimeter cubed, right? What about burettes? Burettes have the good things of the measuring cylinder. It takes a lot of volume and it's also quite accurate, right? So again, there are two good things here. It's accurate, that's the burette I'm talking about, and it measures like a lot of volume. So you can measure you can measure a lot of fluids. Now, what's the issue we have with a burette? The only issue with burettes is that it's time consuming. To set up a burette, you need to put it on a clamp, you put it on a stand like the one you have here in blue, and you have to make sure it's like upright. You have to make sure that the surface is straight. So for all of these reasons, the burette, it's good, but the only issue here, I would not use it. I would only use it if you are like, usually we use it for something called neutralization. Neutralization reactions, the one where you mix acids and alkali. So again, burettes are accurate. You can take a lot of volume, but it takes time. All right. And as I said, it's ideal only to do measurements of when you're doing like what we call neutralization. Again, what is neutralization? Neutralization is when you're mixing up acids and alkali. And that's like mostly what we use burettes for, just because of how much time and effort it takes to set up a burette. Okay. Is there any questions so far? Okay. Now let's try, before we get to the practical or the methods we're learning about today, let's try to do something. Let's try to classify matter. Last week we stated that 3 states of matter: solid, liquid, gas. Today we're trying to do what? Today we're trying to classify matter based on what? Based on its purity. So look what I have here. I'm going to classify matter into pure. When I say pure, this means the entire substance is made up of one type of particles, okay? Here, I'm gonna say impure, or it's a mixture, okay? So that's how am I gonna classify matter today. So what's an example of a mixture? A good example of mixture is something like seawater. Why seawater is a mixture? Because seawater is made up of water and salt, okay? What about pure substances? Pure substances fall into 2 types. They could be elements. What's an element? Basically, elements is what you have like in the periodic table. In the periodic table, you have carbon, nitrogen, oxygen. These are elements, all right? Or you could have what we call molecules. What's a molecule? A molecule is when elements are joined together. If you have like two elements, let's say water. Water is a molecule. Why is it a molecule? Because it's like made up of what? A water molecule is made up of hydrogen and oxygen joined together. So that's an example here of a molecule. All right. I just want to do some further classification here. I'm just going to classify those elements of molecules one step further. So look what I have here. This blue circle, you see that large blue circle outside? This is all pure substances. And we said those could be what? They could be elements, one type of particles, like carbon, oxygen, hydrogen. They could be molecules. Remember our example of molecule, that could be something like water, or they could be compounds. So look at the compound circle. The compound circle is like the smallest one. It's within molecules. It's pure. It's a molecule. So all by default, all molecules are compounds. Sorry, all compounds are molecules. So molecules go into the compounds go into the molecule circle. What's the difference then? Now note, if the particles attached are different, then automatically you can call it a compound. So water, look what I'm going to take the water. I can put the water here inside compound. Reason, it's because there's hydrogen, oxygen. There are two different types of particles joined together. When am I only saying molecule without saying compound? Like when is the time you're only allowed to say molecule and you're not allowed to say a compound? That's when the particles attached are identical. So for instance, something like oxygen. Oxygen, I can only call oxygen a molecule, but I cannot call it a compound. Reason, because oxygen is made up of an O atom, oxygen atom, and another oxygen atom, and they are not different. So again, let me clarify. All pure substances can fall into three types. They could be elements, molecules, compound. If they're elements, then they are just one type of particles, right? Something like oxygen, carbon, all these are elements. If you have particles joined, whenever you have particles joining together, then I'm allowed to call them molecules. If they're joined and different, like what I have here, then in this case, what am I going to call that? I'm going to call this a compound. Badr, you have a question?
Yes.
I'm listening,
Mr. How you said that the oxygen is molecules because the oxygen is not different, and also you said that the water is a molecule and the water is H2O.
You were speaking. Let me just make sure I'm having my speaker. Sorry, but can you speak again?
You said that the oxygen is molecule, not a compound, because they are two O's oxygen without nothing different. But you said also that the water is a molecule, but the water is H2O, يعني hydrogen واكسجين. فهاو بقى ان الاثنين molecules وواحده different والثانيه لا.
Yeah, because do you see the circle of molecules? The circle of molecules is bigger, right?
Yes.
So if it's a molecule, it could be same or could be different. True? But if it's a compound, then they can only be different attached together. Right? So water is a molecule. Let me talk, please. Okay. Water is a molecule and it is a compound. All right? But oxygen is just one type of particles joined together. So I'm only allowed to call it a molecule, but I'm not allowed to call it a compound, right?
Okay, I got it. Okay.
Right.
Thanks.
If you've just joined the class, some people like joined late because of some technical problem. I'm going to send you that first part of the class that you sent right after when we're done, okay? All right, so let's just try something. I have some diagrams here. What I want you to try here, I have like, I want you to classify them based mixture, element, compound, etc. So let's try something. The first diagram, you see that number one thing. What does that look more like to you? Since it's one type of particles, then the only thing I'm allowed to use here in this case, I'm going to use the word element. Again, why? Because they're all identical. They're all the same type of particles. Let's try number two. Do you see what's number two is? Number two, they're identical. Do you see? There are just the same type of particles. So here, I'm allowed to use the word element again. So I can use the word element. But do you see that those two particles are joined? They're attached to one another. So that reason, what else can I call this second diagram, number two? Can someone suggest what would be another way of calling it? Let's try Mr. Ahmed. Yeah, I can call it also a molecule. Reason? Because the particles, identical particles attached to one another. Now, let's take a look at number three. I want someone to figure out what would be the best way to call number three. Yahya?
A mixture.
Two. Reason? Because I have a molecule, I have an element, and they are not joined. See, there's like space in between. So that is a mixture. So number three is a mixture. I'm just going to classify it as a mixture here. Very good, Yahya. What about number four? Could someone figure out like what can someone call number four in two different ways? So can someone suggest the name of number four in two different ways? Adham?
Compound.
All right. Can I call it something else also? Do you remember those circles I was trying to show you there? By default, all compounds can also be called molecules. I can call it compound or a molecule, okay? The last one, what am I supposed to call the last one here? Abdurrahman?
Mixture.
That's true, right? Because I have like two types of particles. They're not joined, they're separate. So that's why I'm going to call number four, I'm going to call that a mixture. Okay? Mixture of two compounds or two molecules. Okay? Is there any question? Now, I want you to try this one here. This is like one step further. We're going to try here to do what? We're going to try based on symbols to figure out if it's a molecule or if it's a compound or if it's an element. How are you supposed to tell? Look, the capital letter, when I see Na, that's one element. When I see Cl attached to it, that's another element. So NaCl is what? NaCl is two elements combined together. They're different. So what am I going to call NaCl in this case? They're two different elements joined together. I'm going to call this a compound. Okay, here we go. Someone's asking, what's the difference between molecule and element? So let me show you the question. They're asking here, what's the difference between molecule and element? Look, my friend, if it's a molecule, then the particles are attached, okay? So the two particles attached to one another, that's a molecule. If they're identical, if the particles attached are identical, then I can call it still an element. So this picture, do you remember that picture I showed you here? That's a molecule and it's an element because they're one type of particles only, okay? If they're different, then I can call it a molecule or a compound. How about Fe? Can someone suggest what is the best way to call Fe? Yusuf?
Element.
Just an element, very good. That's the only thing I can call iron or Fe. Can someone call F2 in two different ways? Hamid?
Yes, is it compound?
How is it compound, Hamid? Because I can only see F and another F, just two Fs attached to one another, right?
Oh, yes.
So what am I supposed to call it then?
A molecule?
Very good. I can call it a molecule or an element because it's just one type of particles. What if it's Br2? Same, right? What if it's Zn? Zn is like one symbol. So what can I call Zn, Yusuf?
Element.
That's an element, right? Finally, I have CH4. These are like two different elements. So for that reason, they're joined. It's one formula. That's why I'm going to call that what? I'm going to call it a compound or a molecule, because all compounds by default are molecules. Okay. Any question? Kindly, if you don't have questions, put your hand down so I know who has a question and who wants to answer. Right. So now we're going into our lesson in more depth. So we're going to look at a mixture that we will face, or we're going to be having almost every lesson. This mixture is what we call a solution. What's a solution? Solution is a mixture of two things. There's always what we call a solute. What's a solute? A solute is what we dissolve. For instance, if I am dissolving salt in water, then in this case, the salt that I'm dissolving, the salt I'm putting into the water, that's the solute, okay? What's the other part of a solution? The other part of the solution is what I call solvent, right? So again, I have solute and I have solvent. Together is what I call a solution, right? Good to give an example. Example would be something like, for instance, coffee. Coffee is made up of water, solvent, solute. Together, we call that combination, or the mixture here I have in, I call that a solution. Sometimes, like only case, if the solvent, if your solvent is water, which is mostly the case, right? Most of the times the solvent we use in chemistry is water. Then in this case, I would call this an aqueous solution. Again, what does the word aqueous? The word aqueous stands for what? Stands for a solution where your solvent is water, right? So for instance, do you remember the salt and water? Salt and water that I have here. Salt and water, that's an aqueous solution of salt, where like you dissolve it into water, okay? Any question? Lily, you have a question?
Yes, could you please repeat that part again?
Which part? Sorry.
From the beginning of the solution. What's a solution?
Lily, I was trying to tell you here what? I was trying to tell you that solution is a mixture, okay? It's made up of something like salt, something you would dissolve, like salt or sugar, or anything that dissolves, and a solvent. What's a solvent? Solvent is what you are dissolving into, like water and sugar. Water is a solvent, sugar is a solute. Together, that's what we call a solution. And in some cases, or most of the times, should say, in most of the times, if your solvent is water, then I would call this solution, what am I supposed to call it? I would call it a aqueous solution. So for short, we call it AQ, right? So for instance, NaCl, like if I write NaCl like this, that's salt. If I write next to it AQ like this, what does that AQ next to it? The AQ next to it stands for aqueous, means the salt has been dissolved into water. Okay?
Okay,
Is this great? Now, we have another word or another term to use here. We call it solubility. Solubility stands for what? Solubility stands like for how much salt you have dissolved into water. Because sometimes you could, like for instance, if I have salt, table salt, it has high solubility. This means what? This means you can dissolve a lot of salt. You can put a lot of salt into water. That means that the solubility is high. Some other cases, the solubility is low, right? So for instance, calcium carbonate has low solubility, meaning that I can only dissolve a little bit of it and the rest won't dissolve. So I would call calcium carbonate having low solubility, or it is insoluble, right? So not all materials could possibly dissolve into water. Some materials dissolve very, very well, and some of them don't dissolve or they are insoluble, okay? Is this clear? Now, let's check something. Let's check like, how do you tell if something is pure? Like if you have two bottles, let's say someone's challenging you. You have two identical bottles. They look exactly the same thing, but they're asking you to do what here? They're asking you to figure out which one is pure water and which one is salt water, and you're not allowed to taste them. So again, the two bottles in front of you, someone's asking like, find me which one is salt water and which one is pure water. And again, you're not supposed to taste them. To do so, we have like one test of purity. How will you test purity? You can test purity by measuring the boiling point. You measure the boiling point, you'll find that salt water boils at a higher temperature. So again, always, salt water has a higher boiling temperature than pure water, okay? For instance, if you have seawater would boil at like 105, 106, reason because of the salt it has, okay? In the same line, if you have like ice, all right, you can change the melting point of ice. Usually ice of pure water melts at 0 degrees. So ice melts at 0 degrees. But if you add salt to the ice, guess what's going to happen to the melting point? Here you'll find that the melting point actually decreases. So keep this in mind. Water, when it has salt in it, it boils at high temperature. And when it has like impurities or salt in it, it melts at lower temperature. Let me show you something. Like here, I have some ice. And as I told you, ice melts at 0 degrees Celsius. But if I add salt to it, check the melting point. The melting point starts to drop. You would decrease the melting point as you dissolve salt, sugar, any solute in the water. So what's the conclusion that we can come up with here? The conclusion is like this. Anytime you put impurities into the water, the boiling point increases and the melting point decreases. So the boiling point will no longer be sharp, fixed points. Okay? Is this clear? Is there any question? Someone's asking, doesn't mean that if they increase the temperature, does that mean that it would dissolve? Let me show you his question. It's a good question. Let me show you. Someone's asking, like, if the temperature is higher, will this affect the boiling point? Yes, it does. Usually, the higher the temperature, the more likely you dissolve salt or sugar into water. You would notice that if the water is hot, you can put more and more salt into it. Now, usually you do get graphs like this one here. The graph you have in front of you is something we took last time. That's a graph of substance that's pure. Do you guys still remember, like we said last time, we said we have solids, liquid, gas. And this line here represents the melting point. Now, this substance here in front of you is a pure substance. What's the reason? That's because look at the melting point and the boiling point are sharp. So this could be like pure water. Pure water, the boiling point will be 100 degrees Celsius, and the melting point would be 0 degrees Celsius. Now, what if it was, let's say someone's asking me like, how much is the melting boiling point of salt water? How much is that's going to be? This case, it's going to be something like a range, right? So you ask me like, what's the melting point or boiling point of seawater? I'm telling you, I don't know really. The boiling point like would be in the range between 100, maybe 105. It really depends on how much salt or sugar you have in the water. It's a range. And the melting point would be like between the range of 0 to -5. Again, these are rough numbers because we don't know how much salt or sugar there is. So again, let me write you a conclusion of what we've done so far. Look, pure substances melt and boil at fixed, sharp, like temperatures, okay? If the substance is impure, then its melting point, I'm writing MP for melting point. What happens to the melting point? Remember what happens to the melting point? Melting point decreases. And boiling point, what happens to it? Increases. And is no longer fixed. What's it going to be like here? Impure would melt and boil at a range of temperatures. Okay? Yeah, tell me what's your question?
It's not a question, but they're saying on WhatsApp, some people are not able to enter.
Yeah, I know, but I cannot help them right now because so many people were able to enter. So just you can manage their way.
That's okay. Thank you.
All right. Thank you. Okay. So let's start with like the methods. So I'm going to show you like few methods of how you could purify substances. Look at my first method. This is the first method, the one I showed you at the beginning. Remember the coffee thing I was trying to show you? That's called filtration. What is filtration about? Filtration is about you. Look at the title. The title, I summarized like the whole thing. Filtration is when you remove an insoluble solid from a liquid. Okay? So let's say you have sand and water. How are you supposed to separate sand from water? Here, you grab like a filter funnel. That's called a filter funnel. Filter paper, and you put the mixture. What is going to get stuck inside that filter paper? You would get the solid. The solid would not be able to get through that filter paper. All right? So one more time, let me show you an example. So here is my filtration. What am I doing here? That's my mixture. I'm pouring it into that filter paper, filter funnel. What am I going to get? All of the solid remains stuck here. You know what I'm going to call that solid? I'm going to call it a residue. All right. And this part here is what I call a filtrate. Okay. So residue is what gets stuck inside that filter paper. The solid, let's say sand will get stuck here and water will pass through. The water is a filtrate and the sand is the residue. Okay. I just have warning here. You cannot filter something that is soluble. So there's no way I can separate salt from water by filtration. Reason, the salt particles are dissolved. They're very, very small. So they're just going to flow through the filter paper. So filtration, again, as it's written in the title in orange, filtration is only meant to separate something that is solid. You cannot separate things that are like soluble. Okay. Now I want somebody to help me out with the labeling, because labeling is quite important, especially when it comes to the paper 6 exam. So maybe we try someone who hasn't spoken today, someone new, anyone hasn't tried today, maybe. Let's try safe. Do you know how to do it, safe?
Yes.
Try, please. So what am I going to call A? A is that glass thing that I'm using
filter
here?
funnel,
Very good, safe. What am I gonna call the part B? Is the part that gets stuck inside the filter paper.
residue,
Very good, safe. And what do I call the water that goes through the filter paper?
filtrate,
Very good. Now I want you to tell me, like, what am I gonna call that paper I put inside the filter funnel?
filter paper,
That's good. And the last thing is just like general here.
conical flask,
Very good, right? Good. So these are the labels we're going to be used in this experiment. Again, I'm just going to repeat this because I see this so many times, this mistake that people think that I can use filtration to separate any solid. The solid has to be insoluble if you are to use filtration, okay? My other example here, let's say I have salt water, okay? And I am interested this time in what? I want, like my question here, I want to get salt out of salt water or seawater, right? How am I supposed to do this? To do this, I need to get rid of the water, all right? So again, let's say this is a flask here containing salt and water. And here I'm interested in what? I am interested in the salt and I don't want the water. Look what I'm gonna do. I'm gonna just take this salt water, put it into this equipment, piece of equipment here. I call this an evaporation dish, okay? Or evaporating basin, just call it evaporation dish. And you heat. As you heat, guess what's gonna happen? The water evaporates, right? And what am I left with here? I am left with the salt, only the salt, okay? So again, this is like, if you've ever wondered, how do you get the salt on your table from? We can get it from the sea. Look what those people are doing. Those people take seawater, they put it near the beach, and they evaporate the water with the sun, and you get that salt out from the seawater, okay? Now, just like what Saif has done a couple of minutes ago, can someone try to label these equipment? Someone maybe didn't speak today. Freddy?
Yes, Master.
If you could just raise your voice so I can hear you.
Okay, so letter A is the evaporation dish.
Evaporation dish. What about B? B is like what I put the evaporation dish on.
Is it the stand? What's it called?
It's a stand with 3 legs. So what am I going to call 3? I call 3 try. Legs is what? Usually I use the word pod, tripod. C is something I put on the table because, you know, like your school tables are made of wood because I don't want to burn the school down, right? I'm going to put something to protect the table from. Usually I call C, Freddy, I call it a heat-proof mat. It's a mat, like a cover, that prevent the table from burning, okay? Do you know what I call letter E? E is what I use for heating in chemistry. You know what I call E?
It's a Bunsen burner.
That's a Bunsen burner. Lastly, that you see that metal thing I'm having here? This is like a network of, I put the dish on and I call it what? I call it a metal gauze. So it's a metal gauze. Metal gauze is just like a metal that I put the object on just to allow the heat and prevents the object from dropping. Okay?
Thank you.
Yusuf, you have a question?
No.
All right. Could you guys again, if you don't have questions, just put your hand down because I don't know if you have a question or you're just trying to answer. Okay? And it takes, you don't know how much effort it takes. I have to do like several clicks to lower your hand. All right. Here I have a challenge. Today we're going to try to do what? I have this sand, salt, and iron. So what you have here in front of you is a mixture of sand, salt, and iron. And I want to do what? I want to separate this mixture. I want to get the iron, the sand, and the salt. I want to get them each separate, okay? I want someone to try to separate the iron. So what would be the best way to separate the iron as?
Use a magnet.
Very good. Thank you very much. So the first thing I'm going to do here, I'm going to use a magnet. With this magnet, I can get the iron. Okay. Step number one, we've done the first thing. We got this iron out. Next thing, what I want here, I want to separate. I'm left now with what? So the iron is done, right? He helped me with the iron. Now I want the sand and the salt. How am I supposed to separate the sand?
Can I answer it?
Can I ask someone else? Because some people are trying. Okay. Sammy?
We should mix it inside water
Very
to
good.
separate the salt and
So my next thing, I'm going to take my mixture and I'm going to put it into water. As I put it into water, salt dissolves. All right. And what am I going to be left with? The sand. So now I have sand and salt water. How am I supposed to remove the sand and keep that salt water? Hala?
By filtration.
Very good, Hala. So I'm going to do this one. I'm going to take my filter funnel flask and I'm going to take that filter paper. I'm going to put it here inside that funnel. And then what am I going to do now? I'm going to pour the mixture. While I'm pouring the mixture, what's going to happen now? The sand here, what will happen to the sand? The sand would basically get trapped inside the filter paper and the salt water will be here. So here I will have salt water. Here I will have the sand. What I'm going to do next now, I'm going to dry up the sand, just dry it up. So I will only have sand. And here I have salt water. The last thing I'm supposed to do here now is what? The last thing, I want to separate the salt from the water. How am I supposed to do this one here? The person, could you just tell me your name, please? Because I can't pronounce it.
You can say Rishi.
Richie. Okay, nice to meet you, Richie. Can you tell me, like, how am I supposed to get salt out of the water?
Through evaporation.
Very good. So my next thing is to do now is to get that mixture. So I have like now a mixture of salt and water. I'm just gonna grab my Bunsen burner and evaporate the water and leave the salt behind. Okay, so one more time. Here we go. This is the sand. I'm gonna put it first into the filter paper. The sand gets trapped inside that filter paper. So what I have here, the sand is here, salt water is here. Just like what Richie said, he's going to evaporate the water, okay, and leave the salt behind. So we've succeeded, right? We've succeeded. We've got the salt separate, we got the iron separate, and we got the sand separate, okay? Someone wrote me the whole procedure. Can we check her work? Let's check what she has written here. She's written like this. Let me show you what she has written. She wrote this on the chat. Get the iron using a magnet, dissolve the rest, filter the sand, and then evaporate the filtering. Very, very efficient, right? She wrote the whole procedure just in like few sentences, okay? Okay, now I have a question for you. This question is taken from paper 6 exam paper. They give you the same thing. So the same thing we've been working on is given to me here. They just wanted you to do what? They just wanted you to first label. We're going to label this part, this one here. And we're going to put the events in their correct order. Okay. Let's start by putting the events in order and then we label. Label is easy. Okay. So look what they've done. They wrote A. A is the first thing, right? So I have mixture of sand. What does sodium chloride mean? Sodium chloride is just like a fancy word for salt. Okay. And what am I supposed to do here? I am supposed to separate them. So who could suggest what would be the next step to be? So what would be the next step to do rather than I'm starting here with this procedure? Maybe someone you could try here, or I ask the same people. Let's try Mr. Adham again.
C.
Yeah, I'm gonna dissolve. So after A comes what? After A comes C. Okay. So I've dissolved in water, right? What would come after C? Now I've dissolved the thing. I need to separate the sand. So what would be the next event now that I want to separate the sand? Judy?
F.
Very good, Judy. So it's going to be F. I'm going to do filtration. With filtration, the sand is here. Salt water is down in the evaporation dish. What would be the next event after F? Who could suggest the option? Anyone could tell me now, what am I supposed to do to get the sand and separate it? Let's try Mr. Yahya.
B.
Very good. I could do option B. B is good. So one option here, they accepted two answers. They could accept you write in B or write in D. Same thing for the next event. They accepted you write in D or B because you could do it either way, okay? The last event, obviously, the only event left here is E, okay? So these are all the things we've done so far today. We just have them in this order, okay? All right, so let's try now why, sorry, they said complete the box. Do you guys know what the name of that box that we were to label here? Box's name, Lily, do you know what the name of it is?
An evaporating dish.
So that's known as an evaporating dish, okay? And they said, why is the sand rinsed with water? That's an important question. So put a star next to it. They usually ask you this question, like while doing filtration, why should I rinse the sand with like nice, clean, distilled water? Reason, if you don't rinse the sand here, you know what's going to happen? Some salt may still be inside the sand, okay? When I rinse the sand, this means all the salt here, all the salt that stay in the sand, all of it would just go through that filter paper, okay? So again, look what I'm going to write. I think I say just also to make sure that no salt is still remaining in the sand. So all the salt has been washed off and now it's inside that salt water. What's the purpose of F? Like, why did we do step F anyway? Like, what's the purpose of us doing this step F? Is, do you know why?
To evaporate the salt.
Step F.
To get filter the sand of the salt.
Very good. So F is filtration.
Filtration.
Very good. To filter the sand or from the mixture. Okay. How could your purity of sodium chloride be checked? So those who've been listening well, I mentioned today one way I could check the purity of whatever substance. Do you guys still remember, like, what is the best way I could possibly determine? Very good. Someone wrote the answer here on the chat. Mohammed said it's right. Do you remember, like, one way we could possibly?
The boiling point.
Habibi, don't speak unless you've been asked to. Okay, please. Mahmoud.
Different boiling points.
Very good. I can measure its melting point. Why melting point would be more appropriate here rather than saying boiling point? Because salt is solid, right? So it's not like really accurate to say like measure the boiling point of salt because salt is solid. So I'd rather say melting point. Although it's not been asked here, let's say it was 2 marks. What am I supposed to write here? I'd say, well, if it is pure, then it will melt at a fixed temperature. Okay. Is this clear? All right. So let's go to our next thing. This time I'm separating liquids. Right. So again, I have 2 liquids and I want to separate them. But those 2 liquids, see the word, there's a new word probably to you. Their 2 liquids are immiscible. What does it mean when I say the liquids are immiscible? Immiscible means they don't mix. All right. So for instance, if you have oil and water are immiscible, meaning that they don't mix very well with one another. To separate a mixture like this, you know what I'm going to do? I'm going to use that separating funnel. So this funnel here, we call it separating funnel. I just want to warn you about something pretty important here. Sometimes in the exam paper, they put the separating funnel like this and it looks like a burette to me now, right? You remember the burette at the beginning of the class? It looks like a burette, but it's not a burette because burettes come with a scale here. So usually a scale here, right? So just be careful. Filter funnel, if it's just being shown to you like this, it would look like a burette. You just have to watch this part and check that it doesn't have a scale because filter funnels are not meant to measure volume. Anyway, here we have 2 liquids. Let's say I'm separating oil and water. The oil is going to be always floating on top. You know why the oil will be on the top? Because oil has lower density than water. And the lower part is going to be the water or the liquid with higher density. So again, this is how the method is done. You would use the filter funnel. You pour the mixture. The water goes first. You know why the water will go first? The water goes first because water is heavy, dense. It goes down first. And the oil stays there inside the funnel. Okay. This particular method is not like the most accurate method of separating liquids simply because some oil might mix with water. But nonetheless, it's quick. It's easy, right? Usually I call this method, guess what I'm going to call this method? I call this method decanting, right? Again, what does to decant mean? Decanting. To decant means to separate liquids that are immiscible, liquids that don't mix well with one another, simply by pouring off, like what we have done here. You could do decanting in a different way. You could just grab like a dropper, take the oil from the top and separate it from water. Let me show you how you could do this. So again, I take a syringe or a dropper and I take the oil out from the top. This is still be called what? This is still called as decanting. Okay. Is this clear? Hala, you have a question? All right. All right, so I'm going now into 2 methods that are quite similar. The first method is known as distillation. What is distillation about? Distillation, you're separating salt from water. You may tell me, like, we already took how to separate salt and water. During evaporation, while we were doing evaporation, we removed the water, right? We got rid of the water. But this time, when I'm doing simple distillation, like what I'm having here, I'm actually doing what? I'm actually leaving the salt behind and making use of the water. Again, This is something you would do to drink water. Let's say you were stuck on an island and you want to drink fresh water. The way you would do it is called simple distillation. Basically, distillation is two things. You would evaporate and then you will condense. So you evaporate the water, but don't stop there. You're going to cool down the vapor and have that water again, right? So again, to do so, what do I need? That's the mixture. I'll heat it up here. So I'll heat up the mixture here at the bottom. So you'll have like Bunsen burner somewhere here at the bottom. The water evaporates, but I'm not going to allow the water to escape. I'm going to run the water into this thing I have here. You know what I'm going to call that thing? I call it a condenser. Condenser, which is meant to what? Which is meant for what? Which is meant to cool down the water vapor. Okay, so basically you will have the water here on the other end. Let me show you again. So here is my simple distillation. What is it like? You boil the water and you condense the steam inside that condenser, and then you will end up with nice fresh water, and all the salt will be left inside that flask. All right. There's little like trick when it comes to simple distillation. It's about the condenser. You need to fill up the condenser in the right way. We always fill up the condenser bottom to top. What does that mean? This means you'll have a hose here. You let the water, the cold water, to go into the condenser, and you let the water out of the condenser from the other end. Reason, if you don't do so, if you like fill it up in the wrong way, you know what's going to happen? That's wrong. What I'm showing you now is wrong. I just want to show you why is it wrong. If you fill up the condenser the wrong way, this section, this top corner, will not be filled up with water. So the condensation won't be efficient if you don't do it the right way. So let me show you again about the condenser. The condenser has to be filled up bottom to top. Reason, if you don't do so, then you will not be condensing the right way. Again, the condensation is to cool down that water vapor. And to cool down the water vapor, you would need to have some cold water cycle running around the water vapor so that you could turn that steam back into liquid water. Let me explain this one more time, just to make sure you all understand it. So again, I'm going to draw it here. That's my flask. Again, what do I have here? I have like salt and water. So here I have salt in water. Okay. And what am I going to do here? I'm going to heat it up. So here I have like some Bunsen burner. Here I'll make a tiny opening. Okay. I'm going to run a tube down like this. What will I have in this tube? I will have that steam. So here I will have that water vapor running like this. Okay. Now, if I don't have a condenser, then that steam will be lost. I want to drink that water, right? So what am I supposed to do now? I'm going to do like this. I'm going to, around the steam, I'm going to I put a condenser. The blue thing I'm drawing here is what I call a condenser, okay? Now, this condenser has to be filled up the right way. It has to be filled up bottom to top. So this is arrow. This arrow means water in, and this arrow is water out. You may ask me, like, why you're so fussy about the way water enters? Because as I told you, if you do it the wrong way, red for wrong, if you do the wrong way, then this corner will not be filled up with water at all. And then the condensation, it's going to be inefficient. So you wouldn't have like an efficient condensation that way. Okay. Sammy, you have a question?
Yes, and this drawing, what's it called?
This is called, very good question. It's called simple distillation?
In the paper you sent, it's called fractional distillation.
No, the next one, the one after this, is called fractional. All right, so the big difference.
Mister, the
There's still
drawings are
one.
messed up.
This is called fractional, the one after fractional, and the one I have here is simple. Okay.
Okay,
All right.
thank you.
You're welcome. And we have Omar. You have a question, Omar?
Yes.
Tell me.
Have you explained the fractional distillation or not?
Still is coming. Sorry, maybe there was like wrong order. So I'm still at simple distillation. Okay.
Okay.
All right. Fractional is coming right after this. Rudaina, you have a question? Or Hamad Mehdi, you have a question? Lily, you have a question?
Yes.
Okay.
How does the condensation process work in the condenser?
Very good question. Look, my friend, water vapor has to be cooled down. Okay. So the water vapor is running from here. You see it? It's running from here. If I wanted to turn back to water, to like water, liquid water, I have to cool it down. You know, like we took condensation last time, we said like if you have any cold surface and you do like just breathe against it, you will have condensation here, right? So I'm just cooling down that water vapor. How am I cooling it down? I'm cooling it down by having water, cold water running around it. So you see that blue thing here? That's cold water just running around the water vapor. Okay?
Okay, thank you.
You're welcome.
Master,
Yes?
so in simple distillation, we use it for filtering water.
Simple distillation is meant for you to drink fresh water. So leave the salt and get fresh water out from seawater. Okay?
Okay.
All right. And let's try to label it. So that's simple distillation we're trying to label here. Maybe someone can help here with the labels. Hala, do you know what I'm calling A?
As the delivery tube?
Yeah, could be delivered to you. I'm trying to name like the whole thing with
That's condenser?
condenser, right? And can
Isn't
someone
the
know
condenser the one above
where?
above the tube?
That's a delivery tube, my friend. That's a delivery tube, but the whole thing here is a condenser, right? Got it? So that's a delivery here. Got it? B is what? B is water in. Remember, you would always fill up the condenser bottom to top, right? That's water out here on the right. I have a thermometer just to make sure that the water is distilling or condensing at the right temperature. I have some Bunsen burner. And it doesn't have to be a flask, what I have here at the bottom. It's just like any container that I will have here. Usually, the thing that I collect here, what I collect, because the process is called, remember, with filtration, what did we call what we collect? We call it a filtrate. Since this process is distillation, what am I calling what I'm collecting this time? I'm calling it a distillate. Again, what does distillate mean? Basically, the water that you have evaporated and condensed. Okay. Any question?
Sir, if for example in simple distillation, if for like part C, I wrote it as filtrate, it would be wrong.
It's not right. It's not right. Reason because you're not filtering here, right? You're doing distillation. Agreed?
Yes.
True. So I'm just gonna have to call it what I'm doing here. Okay. You,
Okay.
Yahya? All right. Now, what I have here.
Mister, I have a question.
Uh-huh.
Do you fill up the condenser from down or up?
Do you see what's shown in front of you here?
Yes.
That's water in. In means what? Water
Really?
in, right? And this is out, right? So bottom to
you
top.
okay. So you
All right.
fill it from up.
Where is up? Where is down, my friend? Here, that's down. That is up, right? And here it says water in. Do you agree?
Yes.
All right. So always fill it up. As several times I said, you fill it up from the bottom to the top, right? What about that fractional distillation thing that I was telling you about? Fractional distillation, you see the title? It says to separate miscible liquids. We took the word immiscible. Remember, it was oil and water. Oil and water is immiscible. We said liquids that don't mix very well with one another. What about the word miscible? When do I use the word miscible? Miscible is like two liquids that mix very, very well with one another. Think, for example, like water and alcohol. Or let's say I have someone puts two liquids like, you know, like the nail polish thing, acetone and water. Those mix very well. And you would never be able to tell which is which because they very, very soluble in one another. How are you supposed to separate it this time? This time you're going to use what we call fractional distillation. Let me show you fractional distillation and then we label. So that's what fractional distillation is all about. You basically mix the two liquids. So where I have the two liquids, I have them there, here. You see the green thing? Here I have two liquids. And what am I going to do here? I'm going to heat them up. Okay? As I heat them up, one of them, the one that has low boiling point, it would go up first. So again, if I have water and alcohol, as I told you, they mix very well, but alcohol, you know, when you put hand sanitizer on your hand, how does it feel? The alcohol evaporates very quickly. Here's the alcohol. As I start to heat, the alcohol will escape first, okay? And what's going to happen now? The alcohol is going to run, just like last time, it's going to run in the condenser. And it's going to drip here at the bottom. See, it's dripping down here. What about the water? The water is left behind. So basically, you really need to keep an eye on the thermometer. Usually, you know, like the boiling point of alcohol is around 80 degrees. It's not like 80 sharp, 78, 80. So I'm watching the thermometer. As the temperature gets to 80, I will find my alcohol is dripping. What about the water? You know, like water boils at 100, right? So as it gets to 80, 85, I have to stop heating. Why do I have to stop heating? Because I don't want any of the water to escape as well. Now, what's the point of this column thing? Do you see that column that I have here on the left? It's called fractionating column. What's the point of it? This is meant for what? This is meant to just make sure, because sometimes some water here at the bottom, some water at the bottom of the flask may reach 100, right? And that water will escape. But since the temperature here hasn't reached 100, the temperature here is 80, remember? That water will drip back. Again, what's the point of the column thing? The column is like, has some broken glass here, just like any broken glass or glass beads, glass marbles. So anytime you have any water that has reached 100, because near the bottom of the flask, you might have very hot water. So some water will escape, but the temperature here near the condenser, the temperature here is not 100, right? So the water condenses and it drips back. So that's the whole point of this column thing, all right? Let me repeat this one more time. I have two liquids, okay? Two liquids that mix very well with one another, miscible. Remember the word miscible, don't forget it. Miscible liquids. What am I going to do here? I'm going to heat them up, all right? until I reach what? Until I reach the boiling point of the first liquid. I said, if the liquid was alcohol, then you wait at 80 or 78, and you find your alcohol starts to drip here, okay? Before I reach 90 or 95, near 100, what do I have to do? I have to stop the heating, turn off the heat, and you would keep the water remains here. The liquid with higher boiling point stays here, and the alcohol goes to the other end. Just like last time, condensers are always filled up bottom to top all the time, no matter what type of condensation or distillation you are trying to do, okay? I think I have people who want to ask. Ahmed Salim?
Mister, I'm still confused about the difference between fractional and the simple.
Very good question. I mean, simple fractional, simple if you have salt and water and you want to drink fresh water, okay? Fractional, you have two liquids. So there's a big difference. When I say salt water, salt plus water, that is what you're trying to drink the water. That's going to be simple, all right? But if you have two liquids, examples like, let's say I have water plus alcohol. What am I going to use here? If I want to separate the water from alcohol, I'll do what? I'm going to do fractional distillation. Okay.
Mister, does the two liquids has to be mixing?
Yeah, because you know what, Ahmed? If they don't mix, then I can do decanting, right? I can just pour off. I don't need any of the equipment. I just pour off and separate, right?
Yes.
You got the point? So
Yes.
decanting is way easier, cheaper, faster. So I won't be doing this anyways. Okay?
Okay.
All right. See if someone else has a question. Abdurrahman? Or I think Freddy, you have a question?
Yes, Mister. Mister, I think the diagrams are switched between simple distillation and fractional.
I can't hear you. Can you write on the chat because I can barely hear your voice? Omar?
Yes, Mister. Is there any liquid that have higher boiling point than water?
Yes, right? You can have, there's a lot of liquid. Mercury, right? It has like the liquid, right? As like boiling point would be like 1,000 or something, right?
Okay. So I will,
If I am to
water-
separate, let's say, water
the
from
water will
liquid
go
mercury,
first.
then water will go first, right? Okay.
Okay.
Let's explain fractional distillation one more time quickly. So what is fractional distillation is all about? Fractional distillation, you have a mixture, you have two liquids, okay? You heat them up and you will have the liquid with a low boiling point. The liquid with a low boiling point goes first, all right? So you'll find what? You'll find that let's say alcohol and water, you find the alcohol goes first, and then it goes down like this, right? We said if you have water boiling at 100 and alcohol boiling at 80, then alcohol goes first. At 80, what's going to happen? At 80, you will have that the alcohol dripping right here, and the water is left behind. I was trying to tell you here about the role of that column thing. The column, I told you, it just meant to prevent any of the water escaping. Even if some drip of water escaped, then what's going to happen? Then that water would just drip back in reason, because the temperature here in the column, the temperature in the column is lower than the boiling point of the water, okay? Let's master the labels. Let's work on the labels. So what am I going to call A? A is a thermometer. B, do you guys still remember what we call part B? That's the weird column thing. the one we've just got to know a couple of minutes back. Let's check with Mr. Yusuf.
Fractionating column.
The fractionating column, B. I have like a flask here. I have, remember the condenser, who knows how to fill up the condenser? So I have C and E. Which one would be the right way to fill up the condenser? Right? Or, sorry, which one is in, which one is out for the condenser?
Out.
Is? So E is in, right? C is out. Agreed? And D is the condenser, right? So this drawing here is for what? This drawing is fractional distillation, all right? Good. Mohammed Hisham, you have a question?
No, thank you.
All right. Someone's asking, let's check his question. Someone's asking this question here. Does fractional distillation work for two liquids that have almost the same boiling point? Look, my friend, there's no way that two liquids will have identical boiling points, right? Close, yes. But if it's very close, then it's not going to be practical. So you really need to have like a range, like 10 degrees or so you can possibly separate them. Because if they're too close, then it's not really possible to separate them this way. Okay? We still have like some time. I have one more method or two more methods. The other method I have here is known as crystallization. Now, crystallization is not like something new. It's more or less most of the things we studied today. Let's say someone asks you to make these crystals that you have here. These crystals is like a substance known as copper sulfate crystals. Okay, copper sulfate crystals. They look like this. How do you make these crystals? The very first thing you would need here is the actual copper sulfate dissolved into water. So look what I'm going to do. I'm going to take some copper sulfate and I'm going to dissolve into water. So again, step number one, I'm going to take the copper sulfate and I'm going to dissolve into water. So now I have the copper sulfate right here dissolved into water. What am I going to do next? Next thing, I'm going to evaporate it. So again, this is the copper sulfate. I'm heating it up, all right, until it evaporates. And then I'm keeping an eye on the glass. See, it's heated and I'm putting something like this. You know what I call this here? I call it a glass rod. I'm putting it into the copper sulfate. What's the point? Because I don't want to evaporate all the water. Again, the secret of good crystals, like those ones I have here, the secret to good crystals is to keep water within the structure of the crystal. Again, one more time. Crystals have water within them. If you want to get nice crystals, large crystals like the one I have here, what are you supposed to do? You need to heat until certain degree. We call this crystallization point. So I'm heating, but I'm not heating forever. I'm keeping an eye on the glass rod. Once I see that I am having like some crystals forming on the glass rod, this is what I call crystallization point, or the point of crystallization. What does that mean? This means you evaporated most of the water, and now you need to switch off the heat. So let me repeat what we've done so far. So far, we took that copper sulfate solution, we heated it up, and we put like some glass rod like this. And we were watching for what? We were watching to see the point where you start to see crystals forming on the glass rod. As soon as this happens, I remove the heating source and I take the copper sulfate. What am I going to do to it now? I'm going to let it cool. What does it mean when I'm letting it cool? I will basically let it stay at room temperature. Okay? As it's cooling, you know what's going to happen? The remaining water starts to evaporate. But this time it's evaporating slowly. There's a big difference between the first step here, while I was heating strongly, and the next step while I'm cooling, because now the water is evaporating slowly. When the water is evaporating slowly, you start to see crystals forming here. Okay, reason, because now the solubility of the salt into the water is less. Last time, when the water is hot, the solubility was higher, but now these crystals are starting to forming here because they no longer dissolve in cold water. So I have now crystals with little water in it. What am I going to do now? How am I going to get those crystals out from the water? I'm going to get the filter paper and filter funnel. And what am I going to do now? I'm just going to separate those crystals. So the crystals will be trapped inside that filter paper. Just to make sure they're nice and clean. So just to make sure that there are no impurities in them. What am I going to do next? I'm going to get some ice cold water and wash them off. All right. Why should the water be very, very cold here? I need some ice cold water just to make sure that I'm not going to dissolve these crystals, because if the water is hot, then they will dissolve and I will lose them, right? I don't want to lose them after all of that effort. The very last step to do now, because they're wet, how am I supposed to dry them? One may tell me, like, get the Bunsen burner and heat them. If you heat them, you will ruin the whole thing. Because as I told you at the beginning, I told you that what makes those crystals look in that crystal form is that there is water inside of it. What makes the structure of the crystal as it is that there is water inside this structure. So what am I going to do now? I'm just going to get them and I'm going to put them on some tissue paper or filter paper, and they would dry safely without causing them any problem. I'll repeat the whole process. Again, what did we do today here in crystallization? Crystallization is a method you are to get crystals from any soluble material. So let's say someone asks me, you have this beaker and you have salted water. Can you get me nice crystals of salt from that salt water? I tell them yes. How am I supposed to do it? Step number one, heat strongly. Until when you're going to heat? You're going to heat until you start to see crystals. Once you see crystals, you will stop the heating and you would let it cool. So again, heat first, cool, then separate the crystals by filtration, wash them with ice cold water. Again, why do I have to wash with cold water? I have to wash with cold water because if the water is hot, you will dissolve these crystals again. Okay? The very last thing to do is you're going to dry those crystals. You dry them with tissue papers or filter paper and you are good to go. Okay? Let's summarize the whole procedure. So we write the procedure or we fill in the blanks and then we see if you guys have any questions, not any crystals. Okay? So crystallization is to separate what kind of solids we're separating while I'm doing crystallization. Should the solid be soluble or should it be insoluble if I am doing crystallization? Let's try Mr. Omar.
Insoluble.
Very good. No, it's soluble, right? If it's insoluble, I would just do filtration, right? Got it? If you have sand and water, you filter, right? If you have salt and water, you do crystallization.
Yes.
Got it? So it
Got
has to be soluble, right? Next thing it says here, first, the mixture until wet. What am I gonna do first? Amar or Rabi?
Yes, Mister.
So what am I supposed to do? What was the first thing we did to the salt and water to separate the salts? First, I have to do what?
Okay. Heat.
Very good. So first step, I have to, about your question on the chat, you can do crystallization for any soluble thing. Doesn't have to be copper sulfate, okay?
Okay.
The mixture until what? What do I call this point where I have to stop the heating? We said you don't heat forever, otherwise you will ruin those crystals. You lose all of the water in it. I'm gonna heat until point, I call this point of crystallization. Very good. Thank you, Amar. All right. Then I reach what I call, so then cool that saturated solution. What does it mean when I say saturated solution? That's a solution very thick, meaning it has very little water in it. So again, what does it mean when I say saturated solution? This is a solution that is very thick. It has little water in it, in this solution. And like you cannot dissolve anything anymore. So you've reached the limit of the amount of solute in this solvent, okay? So again, I'm gonna tell you more about that saturated solution next time, but let's just now accept that this is the point, or this is the solution that has the maximum limit of solutes. Next, what am I gonna do now? I'm gonna do like some washing. I'm gonna wash those, the crystals, and then I'm gonna do what? So I'm just gonna say, filter the crystals. I need to grab them first, and then wash. Do you remember how we washed the crystals? We said, don't wash them with hot water. You'll dissolve them. You'll wash them with
cold
water. Very good. Finally, at the end, what are you supposed to do? You're going to have to dry them with filter papers. So this is like the whole procedure if you're to do crystallization. Right? Who are those people who have a question? Raise your hand. Freddie, you have a question?
Mister, could you just do the 2 and 4 point?
I can't hear you. Can you repeat?
Can
or
you do the true and false part?
Where is it?
It's the next question.
Oh yeah, I'm gonna do it. Why are you asking me from now about doing something that I'm gonna do afterwards? I don't understand.
Because the time is up, so I'm asking you.
No, but my friend, look, I have a plan here, so please don't tell me what am I gonna do next. It becomes like very annoying. Okay. All right. So what am I gonna do now? I want to figure out. These are like summary of the things we have done today. I want to figure out if these lines are true or false. So again, these are things we've done from the beginning of the class till now. I want to figure out if these lines here are true or false. So I have Ahmed Karam.
Yes, sir.
Yes.
Can I answer? Or?
Yeah, sure.
Water is a molecule, but it's also compound, true?
Very good. We said this at the beginning of the class. As long as you have particles attached to one another, like water, remember what the formula of water, H2O? That's a molecule. Why is it a compound? Because the particles attached here are different. Okay, good. You can separate water from salt by evaporation. You have water. You want to drink water. Okay, and you were to separate water from salt. Can you do this by evaporating the water here? Is?
Yes, Mister.
Answer is no, right? How am I, like if I am to drink water from salt and water, can I just evaporate the water? Right? So
Yes. True.
Instead of this, what am I supposed to say here? I can say distillation, right?
Yes, you can separate the salt from water.
Yeah, very good. Now you got it right. So if you are to get the salt, very good. If you want the salt, then the best way to get the salt is to by evaporating the water.
Okay.
Right. Thank you. Now the key word in the third one here is solid. If you have a solid, right? Can you grab that solid by doing filtration or not? Can we try Mohammed Hisham?
Yes.
Is this true or false, the third one?
True.
That's good. Sodium chloride is separated from aqueous. The key word here is aqueous. Aqueous means it's dissolved in water. Can I do crystallization, the method we just saw? Can I do crystallization of aqueous sodium chloride? Hala? Can I do this, Hala?
False.
If you have salt in water, can I crystallize the salt? You think it's false?
No, it's truth. Sorry,
Right. No
I
problem. No problem. Right? Again, you have salt in water. Then the best way to separate salt from water is to make crystals. Evaporate the water, keep the salt behind. Right? Last one, it says liquids are separated by fractional distillation based on what? What does that mean? That's boiling point. Like, does that method of like separating liquids by boiling point, like did we rely on boiling point while we're doing fractional distillation? Omar?
Right.
It is, right? The basic thing about fraction distillation was the use of their boiling point. Someone's asking me about number 2. For number 2, it says you can separate water from salt. It's implying what? You're implying that you can get the water from salt water by evaporation. I told you, if you are interested in the water, then don't evaporate it, right? If you're interested in salt, do evaporation, right? If you're interested in the water, what you should do? You should do simple distillation. Okay? Now, for those people who came late, they couldn't enter like the beginning of the class, I'm going to send you the class right after this, okay? And we have another class on Thursday. I'm going to do the remaining methods, plus we're going to do like paper 6 practice, because this topic here is so practical. So I'm going to be solving paper 6 questions. And I'm going to do one other method we didn't do yet today called chromatography. Okay? So for now, I'm going to let you go if you don't have questions.
Bye, Mr. Thank you.
Bye. Ahmed?
Sir, you talked about the state of matter in the first lesson. So I wanted to ask, if solids like ice and liquid like water, gas is vapor, then fire, what is it made of?
Fire, very good question. Fire is not matter, right? We said the very beginning of chemistry this year, what did we say? We said there are two types of like there's matter, which is a substance, and there's energy. All right. So things around you in the universe could fall into 2 categories, right? Could be energy like fire, could be matter like solid, liquid, gas, right? So fire is energy. Okay.
Mister,
Yes.
why is number 4 right?
Number 4 is, it says if you want salt from salt in water, then you can actually get the salt by crystallization, can't you?
But salt and water is by distillation.
No, if you are to
Simple
drink the
distillation.
water, you have to read the question well. If you are to drink the water, you do simple distillation. if you're interested in the salt, then what would you do? You do evaporation or crystallization, right?
Right.
So it depends on what you want. You want the water, drink the water, distillation. You want the salt, do crystallization or evaporation, right?
Okay, thank you.
You're welcome.
Doctor, I have a question. When he is pointing in the simple distillation diagram on the tube which is inside the condenser, shall I say that it's the delivery tube or the condenser?
Condenser.
Sorry, I didn't listen.
Condenser, I said, call it a condenser.
Okay, thank you.
You're welcome. Okay. Mohammed Kamel, you have a question?
Yes, sir. Will there be a 10-minute exam on Thursday session?
Yes, every Thursday. Okay.
Okay.
Right.
Thanks.
You're welcome.
Master, have you
Yes.
explained anything before simple distillation and fractional distillation and crystallization?
Yes, we did. I said I'm gonna send it to you right now. Okay.
Okay.
All right.
Mister, I have a question about studying. When I go to study, I study like from the papers we do in the classroom, or where do I
No,
study
this
results?
paper you do in the class is only for the class. You can't use it for anything else. Okay. What you should study from are the notes. I send you notes right after the class, right? So study from the notes quickly and solve the homework. That's the best way to study.
Okay, thank you.
Welcome. Aiz?
Yes. Mister,
Yes.
Thursday is not available for me. Can you send the recording?
No, you have to attend. So either you attend or you lose that class. You can't watch it. Okay. So try to attend.
Okay.